The objective of this discussion is to get one puzzling aspect in FTIR. So what happens is, notice you have a simple FTIR setup shown in the left. What you obtain out of that is the molecular absorption spectrum. Okay, which energies are getting absorbed to what extent? For example, here there is activity going on around 3000. Okay, and then there is some absorption going on around 1300, 400, and near 1000 and all of that. So we have a light source that is typically sent through a sample where absorption happens, and that light source is sent through a beam splitter. That is, what roughly happens is a part of it goes and gets reflected from a mirror and reaches the detector. Another part of it actually goes through that, reflected from another mirror. In this case, the mirror is not stationary, the mirror is rather moving, and again gets reflected and arrives at the detector. This signal that you get at the detector, only major difference that you are doing is a mirror motion that somehow captures molecular absorption spectrum. So the real question is, how can a moving mirror give us a molecular absorption spectrum? So the molecules, the bonds are all vibrating. Somehow, so those vibrations correspond to absorption of the light that you send in. Okay, and that absorption is captured using a simple moving mirror setup. This is referred to as an interferometer. So question is, how does this work? Do any of you have an answer right now? Because if you have an answer, again we are done with the meeting. So one thing, okay, if I were to get the spectral information, there is a slow infrared spectroscopy version of this. You will have to take the incoming signal, you will have to split it into wavelengths, typically by passing through a prism, and then you will have to select the wavelength that you want to through. For example, if I am planning to send in the green wavelength or the yellow wavelength here, I will have to put the yellow goes through. I will have to have a reasonable estimate on what I not hear is, okay, what I hear after passing through a sample, what is the I after passing through a sample, and using this ratio, if I know the frequency that I am letting in, I can get one point here. If I let another type of wave pass through, I can get that information, right? But notice already we are having issues with how fine, what is the resolution that we can really reach here and things like that. Process is technically possible. You can let light from a specific narrow range pass through, do it, compare the original intensity and the intensity after passing through the sample, reasonably get the spectrum, get the absorption spectrum. This process is painstakingly slow, and out of the available light, total light, you are only sending a fraction each time to get a point. So this also suffers from low SNR. You are not making use of all the light that you have. You are sending a very small fraction of that each time. So this is slow, this is low on SNR, this is not good. The same thing when you have it in a FTIR setup, all you could do is, so you have the source. So roughly the source, you have a light that is passing through the sample, and what comes out of the sample, all of that put together is represented in the source. So what comes out of the sample after absorption, right? So now partly there is a beam splitter over here. It will partially reflect, it will partially allow light to pass on. So partially things will reflect this side and pass through this side. There is a mirror here that is fixed. So after one more reflection, it will head back. And partially it will reflect, partially it will send. So the partial, a small part of that will show up here. This is path one, path one. Let me highlight it using black. A part of it got, was passed through on this side. Let's see what happens to that. Let's put a different color to that. This goes through. There is one more mirror here, okay, that gets reflected in the mirror, and then partly passes through, partly gets reflected. So the green also arrives at here. Light here at the detector arrives through two different paths. It's 1 and 2. If you want me to make it slightly bigger, okay. So from the source, the second path, the source, the first path. Now at the detector, you have both the signals arriving. Typically, what we get is a interference between these two paths 1 and 2. Two signals together, so you get this interferogram. And when you do a Fourier transform of that, you get the spectrum that you are interested in. Which energies, which peaks are there, which energies are there in this oscillation. This is an FTIR setup. Here, you are not doing one wavelength at a time. You are sending the entire light through the sample. So from the source, you just use a beam splitter, and this motor, this mirror, this moves, this translates, this keeps on moving as you obtain the signal. At this stage, in very, very simple terms, okay, or in signals and system terms, you are encoding frequencies here, and here you are decoding frequencies. You got frequencies, how much of it got absorbed, that information is obtained here. To think about it another way, so if what you are getting is a spectrum, okay, the raw signal that you are getting is roughly, summation of all this sinusoids in the spectrum. Okay, so the raw signal that you have, take one component at a time, add all of them together, superpose them, you get the raw signal. So raw signal is this superposed sinusoid. So the real question is, how does this motor movement give you superposed sinusoids, where different frequencies get affected differently, so that if you take a Fourier transform, okay, we get the spectrum. And this encoding roughly happens here physically. This is physical encoding. Through a physical process, moving the mirror, you encode the frequencies. This is mathematical. Decoding is mathematical. Just do a Fourier transform of that, you get the spectrum. It's a very interesting combination. And the crux really boils down to, why does a raw signal behave like superposed sinusoids in very, very simple terms. Okay, in it, if you look at the raw signal, it will look something like this. The signal that over here, this is shown here, and you take Fourier transform of that, you get the spectrum. So the question is, so how does this mirror movement magically give you chemical, absorption spectrum? So this is a detail that I want to explain, but I would rather make it self-evident, okay, at the same time. So I will try to make it approachable. If you have questions, raise it. I will also try to make it reasonably simple, mathematically relatively accurate. Okay, so first step is, we need to understand what a light wave is. There are two signals arriving at the detector with a slight path difference. Path difference is registered as a net phase in the interfering signals, and the path shows up as the phase. A slight change in location is a slight change in phase. A slight change in additional movement, additional distance traveled is a slight change in phase. So the registered sinusoidal has a phase that depends on what the current path difference is, because it's a moving mirror. And then in fact, I can put this as delta of t, the moving mirror, and then the phase difference is k times delta. The k also shows up. The coefficient of delta is k, that is 2 pi nu. So the frequency information also shows up here. This is the most difficult part. So yesterday night I didn't get sleep. Can anyone guess why I didn't get sleep? Okay, so now Hariharan says due to yesterday's class topic. Yeah, because at least one student says I'm somewhat getting it, I'm not getting it. So that makes me sad, and like that gives me sleepless nights, right? Hey, how could I explain this? I know the critical step even before the thing. How do I get it like in simple terms? There's always a question that is running on in my mind. At the same time, I should also give reasonable justice to the subject we are talking about. There are two paths for light. Let's say one path is this. Was based on the mirror position. Second path can be slightly longer. The total distance light travels in the two paths. The second path, the mirror has slightly moved. It has traveled a slightly longer distance. If there is light of one frequency here, it shows up here, there will be a slight phase difference. That phase difference depends on the extra distance the second path travel, the path length difference, delta. So your interfering wave depend on delta, okay? And notice these are slightly differing by two nearby locations, right? So these are spatially separated. So interfering wave is going to be cos of, say, one is at 0. With respect to 0, another one is at k delta. This is the phase difference between the two. So this is what shows up at the detector. I have put kz. This is you detect the interfering pattern is sinusoidal. Specifically notice if delta is 0, there is constructive interference. So this cos is 1. So I have chosen a cos. The interfering wave is sinusoidal. If delta is 0, I get a 1 constructive interference. So I have chosen a cos. If I had chosen a sine, when delta is 0, I get a 0. I get destructive interference. So I didn't choose that. So I chose the interfering signal. What I received in the detector is a cos of k delta. So what you pick is cosine. And what does this k depend on? Wave theory says this k is omega by c. That is, now it depends on the frequency of what this wave is. Of course, right? If we take the same frequency waves, the source, same source, frequency, the phase difference depends on the frequency, right? This phase now depends on frequency. That's it. And I am moving the mirror, so this delta is a function of time. This delta is a function of time, okay? And this term depends on frequency. If there is only one frequency, I get a cosine as a function of time. If I have more frequencies in the source, I get a superposition of all those. I get a summation. This setup creates two paths differing by a slight path difference that shows up as a phase difference. It depends on time as well as the frequency of the light that is traveling. Okay, so you get superimposed cosines that is shown here, the raw signal. If you take Fourier transform of that, you just get the which frequencies are there, you get that information. Okay, yeah, I cannot make it simpler than this. Now, at least some of you, it should have made better sense when I showed the two paths and there is a slight path difference. It should have made better sense. Okay, now let's plot a couple of things. Let's see, so the signal that you're going to get looks like this. The raw signal that you get looks like this. So notice this is oscillating. I have shown one component, one new bar. If there are many new bars, it's going to be a summation of all of that. Let's move over to Desmos and look at what happens. Notice I have just plotted one cosine, the wave number of 1500. I have made this coefficient 0. So there are two cosines there, but I have only plotted one, right? So this is 1500. Again, there was a question, sir, what do you mean by this thing? So notice in this case, when nu 1 into x going to be 1, you started at 1, you will head back at 1. So when do you arrive at it? 0.00067. If I take 1 divided by 1500, exactly get that value. If nu 1 into x is 1, okay, that is x equals 1 by nu 1, 1 by 1500. The function is repeating again. It was 1 here, got back to 1 here. If I were to do the spectrum of this, how will this look? So this is to make it reasonably realistic. This is in say 1500 centimeter inverse. Wave number 1 by lambda is in 1500 centimeter inverse. So roughly, around 3500, you get OH, broad OH oscillation, right? CH again 3000. So 1500, less than 1500, you get many interesting things. Okay, so this is the wave number. Now let's just add. Okay, hey, if I were to take Fourier transform of this, what do we get? Say technically there is a slight path difference. Now things are constructively and destructively interfering. The path difference is also changing as a function of time. The motor is linearly translating the mirror. Path difference is a function of time. So initially this is constructive interference, destructive interference, constructive interference, destructive interference. So this thing oscillates. This is for a specific wavelength or wave number. Hey, how would the spectrum of this look? If we take Fourier transform of this, how would it look? Fourier transform gives you a frequency content. In this case, there is only one frequency, that is say 1500 centimeter inverse. So how should the Fourier transform look? There will be a spike at 1500. There will be Fourier transform will be zero everywhere except at one wave number 1500 centimeter inverse. There will be one spike that corresponds to this amplitude 1. If I add one more signal here, the spectrum will change, make it 0.8. So now my incoming signal is a combination of two frequencies. So of course, this is still an oscillation. Superposition is still an oscillation. So the second frequency that I added here right now was at 1000. So of course, I can change that frequency and see how these two. There are two different frequency signals, two different absorption going on. One at wavelength 1300, wave number 1300, another at wave number 1500. So the raw signal looks like this. If we take spectrum of this, it will identify the two frequencies. Hey, there is a spike at 1300, there is a spike at 1500. I'm not showing the spectrum right now because I don't think there is a capability of that. But so at 1500, you will have the amplitude of 1. 1300, you will have an amplitude of 0.8. That is what Fourier transform does. So had your signal been this, so absorption going on at 1500 and 2000, you will be getting a raw signal like this. And then, so this signal is a function of time because path difference is ultimately a function of time. Your moving mirror. This will be two spikes. So there will be few things. Okay, this is not all pure interference, and then there is going to be. In fact, if I get it very close to 1500, notice I'm getting beats, right? 1600, 1500, I'm getting beats. Let's say the two signals that we have is like this. Okay, in reality, it's cos A plus cos B. There will be a constant term also. So I'm going to put a 1. There is a DC component in the signal that you get in reality. And that component also dies, is kind of, it's not infinite like this, infinitely long like this. This is kind of localized. You get a signal only at a specific duration. So your signal more or less looks like this. You are going to get a signal like this, a raw signal like this. If you had two frequency components, absorption happening at two frequencies. If you take Fourier transform of this, there will be two spikes. If you have absorption happening at many other frequencies, all those frequencies will additionally show up in this raw signal. Okay, so the transform of this shows you the spectra, which is what you had here. Your raw signal is going to be like this. There could be multiple frequencies in the source. After absorption, what goes in here there could be multiple frequencies that goes in here. Typically, this is a summation, which is what I showed. And realistically, your signal looks like this. Yeah, I showed some of this. So realistically, your signal looks like this. When you take Fourier transform of that, you get the spectrum. How was this possible? There was a path difference due to the moving mirror. That is also a function of time, because the mirror is moving as a function of time. That creates an interference pattern, superposed interference pattern. Raw signal, what you detect is the net interference, net superposed signal. It looks like this. And if you take Fourier transform of that is spectra, that is if you take Fourier transform, you get at specific wave numbers. This is a function of wave number, u bar. You get whichever frequency content is there in the source, that shows up as spikes. Here there are multiple frequency contents, so there are absorptions going on here, there is absorption going on here, here there is mild absorption going on here. All of that is obtained in one go. So from doing one wavelength at a time, looking at its attenuation, getting one point at a time, painstakingly this thing, right? Sampling the spectrum, painstakingly, very slow process. You are letting a very fraction of the signal. You let all the light enter, but you encode frequency content using path difference by means of a moving mirror. What you detect as net signal, net superposed interference signal. Spectra gives you the absorption spectrum. So this is how a moving mirror gives you the molecular absorption spectra. So your mirror, this mirror movement is going to be roughly millimeters to centimeters. So the spectra that you are getting somewhere in this range. And so there is decoding going on here. Say, so when you add two sinusoids, there is a cos A plus cos B, essentially that formula, right? Where B is A plus phi. This is due to a minor path difference, and that path difference keeps on changing as a function of time. So this is what you observe. If you have multiple frequencies, it's a summation of this. So this is what happens in a FTIR. This makes use of minor, tiny movements to encode and decode information. So this is like a grandchild of, in fact, vernier caliper. Okay, with that, quickly, any other questions? And some of you are wondering, is this there in the GATE syllabus? We didn't do anything advanced. This is like sine, right? Omega f c lambda wave number. This is there in the GATE syllabus. Some of you are always wondering, it's there. FTIR is also there in the GATE syllabus. Okay, and all the math we did is there in the GATE syllabus. Did anyone get the crux, or at least have a feel like something interesting is going on? Something interesting is going on. But was there any spark? You got it a little. Hey, you know this dual slit experiment. You have slit 1, you have slit 2. If you have a screen here, what arrives at it, there is a path difference. Based on that, there is an interference pattern. So if you look at any point, there is a path difference for the, this all of you know. But here also you are creating two paths. Here also you are creating two paths. So in fact, it's the same math that I was discussing. Here also you are creating two paths. But that path difference, because you are using a moving mirror, that's a function of time. So the path difference keeps changing as a function of time. That also allows you to capture more frequencies as a function of time. Okay. So this is slightly more advanced than the double slit experiment, where there are two paths. Setup is static. Now you have a moving dynamic setup. It is path, the mirror, one of the mirrors is translating. So you have, there is a path difference as a function of time, and there you have to look at the interference pattern. And my suggestion would be, what happens to a single frequency? Then see, if we put two frequencies, what happens? Just like the way I showed in Desmos. Then if I have multiple frequencies, if I have superposition of a continuum of frequencies, what happens? So three questions. Single frequency, what happens? Two or three frequencies, what happens? Third one, continuum of frequencies, superposition of, continuum of frequencies happens. Fortunately, superposition still works. So you get a spectra like this. Is a very good engineering example. How do you, using the mirrors, you are again getting molecular vibrational energies, right? How do you even do that? This is because very clever engineering that is based on fundamental physics and mathematics. Okay, not an easy setup, but still certainly understandable. If you're still curious about it, I would be very happy, and we'll make it available. Okay, so that, or you at this stage, I would just go Google, not necessarily rely on me. My purpose was to create the spark. Go Google, try to understand it, but I suppose your questions are best. If you ask the right questions, the best answers are there in the discussion we had today. Okay.